All right, I think we're all ready to go here. So, as has been the tradition at ISC since 2003, so this is the 20th year. Man, time flies. Thomas Sterling will help close out the ISC program with his reflections about this past year's achievements and trends in high-performance communities across the entire world. He will be joined, though, for the first time by Estela Suarez, who will look at how those trends project out for the future of HPC. So Thomas Tron holds a position as Professor of Intelligent Systems Engineering at the Indiana State University, or Indiana University School of Informatics, Computing, and Engineering. Tom is best known as the father of Beowulf. These are his pioneering research into community-driven Linux cluster computing that has become the norm for all of computing in HPC. Estela Suarez is the chair of the Next Generation Architectures and Prototypes at the Jülich Supercomputing Center and is also a professor at University of Bonn. And she will provide a counterpoint to Thomas's summarization of these past year's achievements and project things into the future of computing and potentially address the challenges put forward by our earlier keynotes from Dan Reed and Valentina Selipova. Michaela Topher, our deputy chair this year and incoming chair for next year's ISC, will moderate this session and employ a hook if necessary if people go over time.
Thank you, John. And so I'm very excited and thrilled to be here with two dear colleagues, and I'm looking forward to our conversation. For those of you here with us, we will have a little bit of time at the end for a couple of questions. We have the microphone, and we start with Thomas, and then we will have Stella also presenting. Thomas, we are looking forward to hearing from you. What happened this year, and where are we today?
Good afternoon, good evening, ladies and gentlemen. It's wonderful. I'd say it's wonderful to see you, but these lights are so bright. But I can hear you breathing. I'd like to just make an early comment. Watching the cluster competition is always delightful for me, and I learned that the winners, over 100 teraflops on the LinPack. That's really cool. The first Beowulf that I and my colleagues, including Don Becker, implemented in 1994 achieved not quite 100 megaflops. So for those of you doing the math in your head, I'll save you the time. That's a factor of 1 million. Not bad for 25 years. Is it 25 years? All right. Well, this is a new experience for me because I have 20 minutes to tell you what I would have told you in 45 minutes. I am delighted to share the podium with Estela Suarez, and she's much more qualified to talk about the future. So this is the bare bones presentation, but it I think will capture at least an essence. Now, I can't be comprehensive or exhaustive, so this is supposed to be an opinion piece anyway. So I've just picked a few points that I think are either high points or low points for this discussion, and so you may have expected a completely different talk. So this, of course, is the first year, or the end of the first year, of what might be called the Exascale epoch, but not a lot happened in that year advancing the Exascale agenda. We still have one machine, Frontiers, at Oak Ridge National Labs. However, looking forward, we can be a little bit more optimistic. So, and by the way, I'm looking at two different sets of slides, and my one eye understands what's happening in one, and one eye understands. There we go. Okay, we're both in sync. So there is really no big news in this respect, although let me just give a shout out for Aurora and Mari Nostrum, both of which have had challenges getting on the floor, but they are, and they will be, by the next time if I'm asked to come back, I'll be able to report to you. And I don't know where I put that, but one thing that's really kind of emerging from our field is the importance of mixed precision math. And this has actually changed my research just a little bit as well. Now, I think it's important to state, and I will say this in a little bit more, that yes, we tend to focus on the tall poles, the top 10 machines and so forth. But for most of us working in HPC, we're down about 2 orders of magnitude, where the vast majority, well over 90% of the machines on the top 500 list, and by the way, anyone who is a real statistician knows that this is unfair sampling. It's only those of us who actually get on the list that want to get on the list, right? So there's this whole dark world, dark energy, dark mass, and dark computing that nonetheless equals or exceeds some of the accomplishments in the science and industry community in this regard. So we're down in the 10 petaflops, and I'll show you a graph on that. And there's a sense of the graying of the HPC community. Like last year, it's Frontiers, it's Fugaku, wonderful machine, Lumi, and Leonardo. And they're not just copies of each other. Each one has its own special case. And this maybe is a piece of news, but you all saw it coming. I didn't. And that is, we finally have a killer app. For decades, we've been struggling with why should you invest, whichever government we're talking to, why should you invest in HPC? Here's all the reasons. They couldn't care less. And now we have it. And it's this mash of HPC and and AI and ML. And the really big part of this is the AI, because while most of us are focusing on very effective machine learning techniques and deep learning, and we'll touch on a little bit of that, AI has very long tails. And we don't get to talk about that much. I certainly can't in this time, but this is why I think this is the real deal. Briefly, in the US, supporting this, we're attacking the supply chain problem that came out of COVID. And has been disruptive in the industry and in the market. And so the CHIPS Act, is intended to invest a lot of money to correct the imbalance of semiconductor fabrication. Now, I say that, but historically, at least in the US, that meant they took the money away from somebody else. Hopefully not me. And the other thing I'm kind of excited, and I haven't heard a lot of talk about this, is that we may have entered a new golden age in HPC computer architecture. Now, I'm old enough, and there may be 2 or 3 people who also remember the 1980s, AD. And this was a very exciting time in computer architecture, very exciting. So in I wish I could give you a whole talk about the things that evolved in that. I think I have a picture somewhere. But now I'll show you a few machines that are coming largely from startup companies, only about no more than half a dozen years old. And the different techniques are not the normal structures that we're used to. Quantum computing, well, I had to put it somewhere. I'll say something, really. And I want to talk briefly, everything is briefly here, I want to talk about 2 initiatives. There are well over a dozen initiatives deserving to be reported, but 2 I'd like to talk about. So I'll mention the Euro HPC joint undertaking, which is more than a year old. It's not brand new, but it has shown major staying power and it's had already significant impact across the 27 nations of the EU and more. I think the number 33. We'll see. And the second initiative is one that I'd like to talk about, and that is the US's Agile program, which only started since the last time that we had this meeting, and it is focused with a degree of risk on furthering graph computing, which may prove to be very important for the future of advanced and extended artificial intelligence. I thought I had one more here. There we go. Yeah, and briefly, those of you who are fortunate to be here on the first day in the morning, you heard Dan Reed's really exceptional talk, with which I largely disagree. And so I'm going to take this moment on stage to provide a little bit of controversial counterpoint. You can disagree with me, but it'll be fun for me. Okay, so deja vu. I could have made this slide a year ago. These machines are exceptional. The US, Japan, EU, I don't quite know how that works, but Lumi, of course, in Finland, and Leonardo in Italy. And I've got nothing more to say about that. I mean, we said it all last year. They're really good machines, and of course, they're at that very peak that's allowing us to do exploration via computing, whether it's simulation or it's data analytics. It's still fantastic and powerful. Now, this is the point I want to make. I've been doing this analysis now for years, but it always comes home to me that the vertical line you have is the one we talk about, and it's like 9, 10 machines at most, the top 10. And the other 490 machines, they're along that horizontal line almost. And that's where most of the real heavy lifting, the HPC computation takes place. And that's where improvements really bring home high impact internationally and across the science and industry technologies. And so, hey for the little guys, of which I certainly am one. The killer app. I don't think I had heard the phrase large language models a year ago, or LLM. In fact, when I first heard LLM, I really thought they were saying LGM, which stands for Little Green Men, and I thought the middle L stood for lime. So that would work. But in fact, looking at this, it's a significant and almost constructively disruptive step in using neural nets, which are trained on very large amounts of data, but they're unlabeled. They're unlabeled, and let's face it, the worst part of machine learning is that you have to already tell them the answer, right? The approximate answer. I know people don't like to hear it, but supervised machine learning is interpolation. And so you're finding the points in between. Now, two major components to this are self-supervised learning, which is sort of someplace in between supervised and unsupervised. So self is between nothing and un. And the issue is the ability to absorb, to assimilate very large amounts of data which are not purely accurate, are not precise. And this opens up a whole wealth of alternative environments. Now, I said maybe we're in a new golden age of supercomputing. I could have shown you 10 slides filled with the names of various ones. Cerebras, it's cool, right? Wafer scale integration. I knew it was going to come probably after my death, but I knew it was going to come. It just made sense. And their second generation machine, and I have to check here, the wafer scale engine. Okay, I got that. 850,000 cores, which is a big number. And then Graph Core, and I'm still trying to figure out Graph Core. And I think the problem is that when they talk about graphs, they're really talking about data flow, not data graphs. Now, somebody can yell out and say, I got it completely wrong. But they've developed their IPU, or Intelligent Processing Unit, and their machine, Colossus. Now, Colossus, that sounds like either something from a science fiction movie, The Forbidden Project, or something at Bletchley Park in World War II. But I guess, there's a timeout on this. Oh, excuse me, here I have one self-serving, and I almost forgot. And a third, I would hardly say competitive, but is something with which I'm affiliated. And this is a small company, Simultac. And we're developing an active memory architecture. And no, I'm not going to do an advertisement for this. But this is under the Agile program, which I'll talk about a little bit more. See, I told you quantum computing. So I didn't know what to say about quantum computing, right? I mean, I could tell stories about Feynman and so forth, but so I just grabbed some what I think are key pieces of evolution that come out. And the first one that caught my eye is the Osprey processor. Now, this has actually been in work for a while, but IBM recently announced 413 qubits were, and here's the verb, accessible. I don't know what accessible means in the world of quantum mechanics, but okay. And when they get it right, it'll be 433 qubits, which is, relatively speaking, a lot. Now, they're looking forward, and they're talking about multiple different machines with over 1,000 qubits in it at some time in the near future. They're being unspecific about that. There is an important piece of work that's being done at Jülich, and that is understanding how to move away from research platforms and work with platforms which are, in fact, are good for industrial grade computing. And so they're worrying about the integration. They use the term hybrid between classical and quantum computing. The thing is, what are the algorithms, and how are the algorithms put across these two very distinct classes of machines, neither of which can really do the best job possible without the other? In the US, there's a National Quantum Initiative Act that didn't start this year, but they're establishing 5 centers at the Department of Energy labs, and they're supposed to be, in the most vague sense, working on advanced quantum information science. But still, there's 2 challenges that we all face in quantum computing, and one is achieving quantum supremacy, whatever that means. But the other is decoherence. And decoherence, meaning no disrespect to those of you in this room who are working quantum computing, decoherence is really the biggest challenge. And if you get rid of that, then you may have to add times 10 to times 100 more qubits just to get it right. And I push the button. Here we go. Now, let me first just briefly bring up a Euro-HPC joint undertaking. It is really great to see an initiative that is, in my view, well-planned, especially when you're dealing with, 24 or plus nations, all of which love each other, and recognize that there are multiple challenges, which are distinct in many respects, but nonetheless are mutually in their own right coherent, right? And Euro-HPC has been doing that. And again, one should give, and yes, they have lots of slides. There are a lot of politics involved in this, but I don't have enough time to share that with you. There are 33 member states and associated countries. I don't quite know what that means. It's all the entire European Union. And then I should give a mention for these other private members, and that's the European Technology Platform, the Big Data Value Association, and the European Quantum Industry Consortium. So they're involved too. Now the funding, I think I captured the number 3 billion, but I may be off by a factor of 2 here, because there are matching funds from the participating countries, and there are other sources as well. So it's very complicated, and I don't care. But the thing is that this is a well-established, well-funded, well-organized, and well-managed initiative. My congratulations, especially since I'm not coming from Europe. US. Okay, US, here we go. Agile. It's a terrible acronym, and I don't even remember what it means. But what's really cool about this, and it's like the best program I've ever been able to participate in, there are 6 different performing teams. I think I can get this. Qualcomm, Intel, and AMD from the industry side, and University of Chicago, Georgia Tech, and Indiana University on the academic side. Each of them are partnered with others to devise very complicated designs. I'm not going to read the blueprint for you, but if you do quickly scan it, you'll realize that the foundation principles that are assumed to be component ideas and implementations in these designs, they're already sufficiently radical that they do not overlap significantly with conventional computing. High reward, innovation, that implies risk. And my other comments in a moment will be about the importance of risk. Right? But first, I want to pause for a moment, and I think we should acknowledge a recent event. I will hardly say it's sad, but it's notable, with the passing of a giant in our field. And it's, I don't use that word lightly. Recently, Gordon Moore passed away. Do I have to talk about him? Of course, he was one of the founders of Intel, and he was also the, creator of Moore's Law, although he denied at any time that he called it a law, but he was kind of outvoted by the rest of us. And indeed, Moore's Law is a household name, at least in all of our households, right? He and his wife, Betty, did establish a philanthropic foundation. What came out of this? Well, the microprocessor. I remember seeing my first 4004 microprocessor on a board in like 1972, maybe 73, and I thought my career was over because they had already done it all. And in some way, Gordon is the spirit of modern HPC because we depended on that exponential growth. All right, so I'm running out of seconds. Let me simply say that Dan Reed's keynote was great. I hung on every word. He and I have talked about, we argued about it since then. And in an overly simplistic way, he said, if you want to change the future, follow the money. Now, he'll disagree that I've adequately captured it. I'll accept that. But to do that suggests limits to the exploitation of knowledge, which includes some from the future, the expectations that we ourselves are driven by, and it's limited by the market of the present, not of the future. It assumes that the future will be the present with some incremental changes. But evolution doesn't work that way, and I hate to break it to you, but we're all a product of evolution. Evolution is actually not about the winners. You know what happens to the winners in evolution? They go extinct. When something, a moment, occurs, and it's the losers, the outliers, the drifters of each species that are sufficiently generalized, although not terribly optimized, that are able to then fit into new ecological niches. As I say on here, ask the mammals. In my view, true evolution of our field occurs from inspired motivation, challenge and opportunity, or recognized opportunity, vision and imagination, and creativity and innovation, and yet risk. Sometimes it takes revolution to create a new real world. Now I know I'm out of time, and they're getting nervous. I'm almost there, folks. So I know that's a lot of words, and I wanted a visual metaphor for this point, this difference between incrementalism and imagination plus risk. And I may not have succeeded, but here's what I came up with. In case you couldn't guess which was which, I put the labels on there. So, the picture on the right, it never gets old. Last slide. But the seriousness is simply this. Are there, in fact, is our field, is the history of our field, the culture, the trends, does it in fact serve or reflect the points I'm making, a counterpoint to what I'm accusing Dan of? And so I struggled with this, and last slide, this is what I came up with. No, that's not what I came up with. Let's try that again. Each one of these is a data point in the history of high-performance computing, I'll argue. Each one of these was a disruptive change that was not foreseen, was not incrementally derived. Each one of this has a really great story associated with it, some of it a little personal, and I therefore claim that punctuated equilibrium, which Dan did state, and the risky innovation that drives that is in fact a necessary component to what has and will succeed in the future of HPC. Thank you very much.
Thank you, Thomas.
I'm sorry,
Thank you.
a little over.
And so thank you for showing us where we are now and doing that with a smile and a little bit of irony. And so now let's look at the future and where we will be today, tomorrow. Estela.
Thank you. So let me start to see where we are now before we get into the future. So for the last 14 to 15 years, the whole HPC community had the common goal of getting to the exaflop mark. And this was achieved last year with Frontier, with the first Exascale system, which is a huge achievement. The question is now, what is next? What will be our next goal or our next goals? And before we too quickly say Zetascale, maybe we should make a step back and realize the world in which we are living, the world in which HPC is embedded and what is going around it. So for the last years, this world has been kind of hustled with a number of events, with the crisis of COVID, with the geopolitical situation in the Ukraine, and the impact, and also, of course, with climate change, which doesn't have a date there because it's a continuous threat. All those things have an impact on HPC. We are all well aware what happened in 2020 with microprocessor shortage, with higher prices in technology. With the Ukrainian war, we experienced a huge rise in energy costs that in some centers it actually led to reduced operations. And where with the climate change, there is a new focus in society that makes us to basically justify the use of energy and the use of resources, of natural resources that we are doing. In the face of such challenges, HPC has always replied, and I hope it continues doing that through innovation. And what I'm going to go through in the next few slides is just some highlights, some cherry picking on research and trends that I think are interesting and might be bringing some solutions, in particular trying to make our systems more efficient and increasing the scientific output. So speaking about innovation, let's start by the processing side. So we see a growing diversity in processing units, from the many core, multi-core CPUs we are all familiar with, to a huge number of accelerators, graphic cards, vector processing accelerators, FPGAs, and even custom ASIC implementations that aim at accelerating a specific instruction, and very often recently in the AI context. Why does this happen? Because we are trying to achieve performance and we are trying to achieve efficiency through a specialization. And the question is, with all this diversity, how do we put them into our HPC systems? How do we put them at the service of our users? There are different approaches, and I will speak first for what I know most, that is the modular supercomputing architecture we use or we developed in Jülich, and that is the basis for the first Exascale system that will be deployed in Europe. We call it Jupiter. The idea is we will have a CPU cluster where the focus is on achieving high memory bandwidth, attached to a GPU-based booster, so an accelerated system, and that's the part that we scale up to the exaflop. This is, of course, then complemented with a hierarchical storage, and this basis configuration, the target is that an application that today runs in our largest system, that is the Jubel's booster, will run 20 times faster, will have a 20 times more performance when running on the full Jupyter machine. So the idea of this architecture is you have different modules. Each one of them tries to be relatively homogeneous internally, but by attaching different architectures together, we build an heterogeneous system. And can be extended, so we have for special purposes like virtualization, or even future technologies like neuromorphic or quantum computing can be then added there. So speaking about quantum computing, Thomas mentioned it before, there is a huge investment in Europe in the integration of quantum computing and HPC. And what you see there are just some installations that are planned in the near future in different sites in Europe, in 7 sites, and that they will all be federated with each other so that, well, the idea is you have different sites will have different quantum technologies. There are many different approaches for quantum computing, and by federating them all together, a user can try different kinds of machines and find out which users are more suitable for which kind of technologies. In parallel to that, there is a research agenda that you see there on the ballots. I will not read through it, but that has very aggressive, targets for 2030 for this time frame. So I was speaking about generally heterogeneity and about this modular idea. Other places are doing this differently. So other places are looking at things like rack-level disaggregation. Currently, you have a server configured in some way, some CPUs and GPUs and memory, and you build your rack by multiplying this several times. Disaggregating this would allow that you have the components, let's say, individually, and you can then pull and compose depending on the needs of the users, and depending on the specific applications, you might have many CPUs for ones, many GPUs for others. This is possible with some new network technologies, such with CXL, that allows for memory coherency across this larger machine. And in the near or farther future, this might be even more interesting if you include there silicon photonics. Now it comes. So silicon photonics, we are using optical cables to achieve long distances already now, but the goal would be to get them closer to the processing unit so that the translation is done less directly from the electronic to the optics, and then you can move up through the optics through the rest of the system. The integration can be different. You see there are some examples, so on-board, co-packaged, or on-chip. But you can achieve, first of all, better energy efficiency because you save the transceivers to make the translation from electric to optical. And you can also get higher bandwidth. You can transfer several packets at the same time using different wavelengths across the cable. And this can be applied then to this rack-level disaggregation, so you can have these pools of resources at the rack, and all of them integrated in this optical fiber, optical network. So now, that's heterogeneity at system level. We also have heterogeneity at chip level. We are moving from the a monolithic silicon piece of silicon that created the large processor to splitting it into several chiplets and interconnecting them with each other to build a larger processor. The interesting thing of doing that is that it opens the opportunity to integrate chiplets from different kinds of technologies, CPUs, GPUs, vector processing units, memory, and build your own chip depending on the kind of use cases, depending on the kind of applications that you have. This is not really future, this is already there. We do have from AMD, we have with NVIDIA co-packaged CPU plus GPU together, and that will open new opportunities, new ways of using these devices. Another very exciting field that is getting a lot of attention, if this replies to me now, is RISC-V. So RISC-V is an open instruction set architecture, and the fact that it is open lowers the entry barrier for new players to come with new ideas. So now university groups, small research groups, small companies can maybe come with a brilliant new device, new chiplet that can be co-packaged with other things and makes it cheaper for them to produce. So it's used mainly up to date in the embedded market, but there are many designs or several designs that are addressing HPC coming up. And within Europe, there are development plans that started already a few years ago with the European Processor Initiative that is developing an accelerator for very long vectors. And further investments are coming up with a call closing actually the next days. So I spoke a lot about hardware. what is the consequence of having all this heterogeneous hardware on the software side? This consequence is a more complex software stack. And if you just look it from the perspective of the programming model, if you just look it from the perspective of the user, means that it has to decide which is the programming model I use depending on the device that you want to use. And this decision can be even depending on the vendor that provides this device. There is a lot of development and research going into the direction of trying to decouple the concerns, trying to ensure that only the lower part of this stack that is here in yellow needs to be optimized to this specific hardware, while the upper layers of this stack can remain as hardware agnostic as possible. There, the layers should have standardized APIs between all of them, and of course the picture is simplified. You will have things that go from top to bottom, but always trying to decouple the front end from the back end to keep things evolving separately. One thing we haven't solved yet is when you have an application there that tries to run or runs simultaneously on different kinds of hardware, each of them with their own frequency, their own pipelines, their own execution method, you have to take care of load balance. And that is, we will see how we address this problem in such a highly heterogeneous systems we are seeing coming up. What happens on the application side? On the application side, regardless of worrying how to port their codes to all this heterogeneous hardware, there are also lots of things going on. They are moving towards digital twins, so trying to involve and to include in the simulation as much aspects as possible of the overall program to represent it as accurately as possible. And this leads to very complex workflows. So typically you need a model to simulate each part of the problem, and you need to couple these models together. An example is on the climate sciences. You have a model for the atmosphere, a model for the ocean, a model for the vegetation, and these things interact continuously with each other and intercommunicate. These complex workflows also include more and more AI components. One example I show here is also is an AI model that is done together with a climate model based on basic principles on physics, and tries to learn from the evolution of this climate model what are the processes going on, and is used then to interpolate via machine learning in the spatial and in the time direction. So you can therefore achieve predictions for a local place and a small place, what will happen if a stream event might be coming up. Last but not least, I wanted to mention also mixed and reduced precision. That's also there a potential to increase performance, get much more performance from the same hardware by giving up on the double precision whenever it is possible, and also this helps achieving a better energy efficiency. Now, these complex workflows I was speaking about, how do they run in our HPC systems right now? Well, they run something like that. So it's quite a static way of allocating the resources. So the dark boxes are the really execution time of the different steps of the workflow. The light boxes is the reservation window of the resources. So there is a lot of place where some resources are waiting for things to happen. They are idling. What some of us are trying to do is to make this scheduling of resources much more dynamic so that the window of allocation of specific resources is equal to the time they are being used. And here, the goal is you don't accelerate the individual application. This will still take the same time, but you maximize the use of the hardware. You increase the throughput of your machine. At the end, you increase the scientific output of your machine. So my almost last technical slide is this one here. So the idea is, how do we optimize our machines? So I want to go back to the one thing that Dan Reed mentioned on Monday that I really liked a lot, the comparison with the aeronautic industry. They are not trying to get any faster. They are trying to optimize their technologies. And I think that we are at the point that we need to exactly go in this direction. So how to maximize the output of our HPC systems, how to improve or optimize for performance, and at the same time for energy efficiency. That's a very complex problem because all these things are, of course, interrelated. And because the systems we have are so complex that just predicting how fast an application will run becomes very difficult. So we need something like coupling between a large system model, precise model of our machines, including the infrastructure, and an end-to-end application performance models that helps to correlate between the system metrics and the application metrics to find the sweet spots there. So only then, when we have quantitative data, we can take the right optimization decisions. Otherwise, we are flying blindly. So now, to conclude, I want to come back to the comments I did at the beginning. Yes, HPC is suffering from the global crisis situation that we are encountering more and more frequently in the recent years, but it's also crucial to address these challenges. I will not give any example about COVID. I think there were enough in the last 2 years on that. About the Ukraine war, I just want to mention that finally, because now it's really painful since the last year, the computer centers have started to apply all the measures they have at their hand to reduce the energy consumption. And it shows that it pays off and it is possible. At the same time, also the community has been trying to help the Ukrainian scientists and citizens that are the real victims of the situation. And I just wanted to give one example from the radio astronomy community, from LOFAR. There is a radio telescope in Ukraine, it's there on the northeast on the map, that has been seriously damaged during the war. And the researchers, beyond just losing their instruments, they were very concerned to lose also the scientific data that had been collected for the last years. They raised the alarm, and the LOFAR community, this is a radio astronomy community, immediately decided to open their long-term archives. One of them is at Jülich, to collect the data, to make a backup of all the scientific data and ensure that this is not lost. Last but not least, on the last challenge, the climate change. It's obvious, I think, to everyone that HPC resources are necessary for climate and Earth system modeling. And only having this, we can do predictions for disasters and take measures to prevent them. One very large and very important project in the European landscape is the Destination Earth project. It aims at doing a digital twin of the Earth so that it would allow to monitor the effects of both the natural and the human-made actions on the climate, anticipate extreme events, and therefore enable triggering the policies for climate-related challenges. There is another example I put here that's not from the climate, but is from the earthquake field. This is work from the Berkeley lab, where they simulate an earthquake on the San Francisco Bay Area, and you see on the left how the seismic waves expand, and on the right, what is the impact on the infrastructures of the city when they receive these seismic waves. This is the highest resolution earthquake model that is available today and will be made publicly available to the civic planners so they can plan also the changes, the necessary changes on the infrastructure to prevent the worst when such an earthquake event arrives. Last, I want to conclude with what, let's say, is my wish list for the goals for the post-exaflop era. So first, we are all, or most of us, pay with public money. So HPC is a public-funded, mostly public-funded research. We need to give practical solutions, practical answers to the societal challenges, and measure the success, measure the performance of our machines on scientific throughput. From the system perspective, we need to achieve a full system view in which we can quantify what the applications really need, and it just does not help asking the developer, we need to quantify it. Enable that through a dynamic orchestration of the resources, we expose to each of those users, based on the requirements, the kind of machine that is optimal for their applications. And last but not least, we have to be much more efficient both for the applications or for achieving the results, and also the machines themselves have to become more energy efficient and reduce as much as possible our CO2 footprint. And with this, I'd like to thank you, everyone that helped me to put this together, and also all of you for your attention.
Thank you, Estela. We are at the end of this session. We have been presented with great insights. Thank you so much to our speaker. I would like to take 2 minutes if there is any fast question in the public attendees. Otherwise, I would like to challenge you both once again. And Estela, you told us your list of wishes, which are fantastic. What could we do wrong? And we should be very careful not to do. We will meet here in 1 year. What is that you don't want to see?
Well, I would say I don't want to see business to run just as usual. So think like, let's do the same things we have been doing all the time. So we need really now to get into action. So we need to realize that we all are also part of a global picture. And when we were speaking about the young people, get them attracted to HPC and so on, I think one important aspect is also how does HPC help to solve those challenges that they see affecting their lives and their future.
So great insights. Thomas, what should we do? Absolutely. You will be here next year and you will tell us, great job, you did what I told you. What should we do?
Well, it'll take more than 1 year.
Well, small step, one at a time.
Yes, like the philosophers in Hitchhiker's Guide to the Galaxy, I have job security because I can always look forward and say what we're doing wrong. What do I change? Strong scaling. Real AI, not this midpoint machine learning. Sorry, but von Neumann architecture is dead. Dynamic control, not static compiler time control, to do what is being discussed, to gain levels of efficiency through the exploitation of runtime information. And I have 5 more fingers, but I'll save that for next year.
So we are taking notes, and we want to meet you here again next year, and we want to check whether what we shouldn't do or what we should do has been at least partially, let's say, but I want to be positive, fully executed. So thank you so much, Estela. Thank you so much, Thomas. Don't go away because there is still a little bit for all of you, but I want to thank again our fantastic speakers. Thank you.
Thank you.
Thank you.